Max Henderson from Rigetti, and I think he's probably got the best title of all the talks. He'll be telling us about the quantum pigeon sinks, which I'm sure you're all curious to know what the heck that is. Please.
Awesome. Yeah, so glad to be here. This is not the only poorly worded pun that you'll see in this presentation. I think I still might have the clumsiest portmanteau for a quantum algorithm for QML. So, but you can be the judge of that later. Briefly, just as a background, I'm really passionate and I love quantum machine learning, and I feel like I've had an interesting perspective, both coming at it from the quantum side as well as the classical side. So my PhD thesis was doing biophysical neural networks, which, if anyone thinks deep neural networks are hard, believe you and me, they're great. It's great to not have to worry about how a neuron is shaped and things like that. Just pretend it's a simple node and blah, blah, blah. So I ended up being a data scientist after graduating and worked at Lockheed Martin, did some work at JP Morgan in New York as well within the bank, doing really classical data science applications. And at the same time, I've been investigating quantum algorithms for doing optimization and machine learning using near-term quantum devices since 2011. So kind of simultaneously, there's this really interesting coming together with QML where you need to ideally have a bit of verse in the classical data science to understand where the applications and use cases are, as well as obviously a deep understanding of how quantum computing fits in all of that. So this talk is really going to be broken down into three major chunks. This picture kind of can show what those three major chunks are going to be, which is a good time to talk about Rigetti in general. So for those of you who don't know Rigetti as a company, we are a full stack quantum computing company. What does that mean? Well, if we stack up, starting at the quantum hardware at the bottom, all the way up to developing quantum applications algorithm at the top, we have different parts of our company that are working on all areas of this stack. So we're going to talk at the beginning sort of about what Rigetti is doing in the hardware space, and then transition to talk a bit about our software, what's happening in the middle, and then finally, being that, again, this is a QML conference, focus on some particular stuff we've done in the machine learning space, which is a bit of my expertise background. So it's always challenging giving a full stack talk when you're only an expert in one part of the stack, but I'll do my best. So yeah, in terms of hardware at Rigetti, so what are we building? So Rigetti still fundamentally, I would say, is a hardware company first. They're trying to build the quantum hardware that's going to provide quantum advantage. This is a cool picture of the fabrication facility in Berkeley. If you're ever in the Bay Area, give us a shout and we can give you a really cool tour. But there's some incredibly good quantum engineers that are really trying to figure out how to improve the fundamental devices that we'd be using to run our software on top of. So that's the macroscopic view. This is like the small view of what actually comes out of that big fabrication facility. We're building these superconducting quantum processors with a particular architecture that we'll show here as well. And again, I'm not a hardware guy, but I know there's a couple key things you want out of your quantum hardware. You want to make sure that your qubits are having longer and longer coherence times. Means that they're not falling into error regimes. And you can see here a little bit far away, but back in May of 2018, these are kind of the pink coherence times up until now in July, the green of this year. And you can see across all these different qubits, basically the technology has improved where we're getting longer and longer coherence times out of our qubits. We also have some cool technology for doing on-chip isolation, so trying to reduce crosstalk error as well. And finally, the other thing that you guys will probably hear about a lot is 2-qubit gate fidelity. If that was at 100%, that means your 2-qubit gate is perfect. Obviously, nobody's getting quite there yet, but we're getting into the 99 point somethings, which is good, and are constantly pushing that to get lower and lower error rates. So these are kind of the three takeaways, I guess, on the hardware side as that's progressing. We have a scalable architecture, which we're using. This is a picture of our Aspen, which has 16 qubits. Each of these nodes represents a single qubit, and the lines between them show qubits that can have interactions with each other. And we are constantly increasing the size of these. So the next 32 chip would look like this. And again, we'd be using this scalable sort of growth to eventually get to 100 quantum chips with over 100 qubits on them. Yeah, we think that there's been really good design for how these things can scale out, and up until much larger qubit chip sizes, this should continue to scale rather nicely. So that's a bit of what's happening on the hardware side. We can talk then about what's happening in the software world, where these guys are nice and shaking hands with each other. So this has already been talked about a bit, but there's been, within QML and within quantum computing in general, there's been a lot of theoretical algorithms that have some nice properties, some of them having exponential speedups, notably Shor's. But obviously everyone in this room that's messed around with practical quantum computing knows that you need massive numbers of quantum resources to execute these algorithms. For instance, like Shor's in this case would need over 10 million error-corrected qubits. So we're not going to be doing that in the near term. And like has been said in this talk a few times by Maria and others, really what we're doing in this near term area is going to be various forms of parameterized quantum circuits for either optimization, for doing chemical simulations, or machine learning applications. So this is kind of the area that we're focusing on, and this area in particular also has a really strong hybrid component. So again, you're never going to be running 100% of your algorithm on a quantum computer, and there's going to have to be a pretty tight integration between the classical and the quantum side to really squeeze the performance out of these devices. So like I said, the future is hybrid, and Righetti is really much more focused on sort of trying to find quantum applications with potential advantages, which means that you have to really optimize not just the quantum performance of the hardware, but also the classical code that we're integrating with it. So again, there's sort of three, I guess, main things that we've done on the software side to try to have this tight integration. All of these three things here: co-location of between the QPU and CPU, so basically trying to put the classical and the quantum resources close together to get speed up. Parameterized program compilation, so basically reducing the total number of cycles you'd have to send stuff back. And also active resets of the qubits, so basically trying to speed up how quickly you can use them again. Are all some improvements that have led to something like a 30x improvement in terms of speed for running these things via the cloud. This is a more detailed breakdown of how these factors end up improving speed. But overall, again, I guess the key message here from the software side, just like the hardware, Righetti's been taking some really active steps into trying to improve, again, how quickly people can do experiments and make that whole process more efficient for research. This is a different sort of graphic, again, of how this sort of works, but we have a couple main products. We have Forest, which is developed for doing various toolkits. These allow people, again, to use our hardware, run different programs, and it is accessible via our quantum cloud services, QCS, which we know is a good name because some of our friends at IBM have also started using it. So we're, I guess, QCS Classic now or something. But the other, I guess, thing we could talk about briefly is that we also have a nice PyQuil wrapper. So for those, again, coming maybe from the data science world that are really used to writing things in Python, this is a nice wrapper that allows you to, again, do Rigetti integratable quantum experiments in Python, which is a lot of people's language of choice. So, okay, gotten through the brief hardware description and talking a bit about the software at Righetti. Now we can actually get into talking a bit about what Righetti's done in the QML space. This was shown by Maria at QTML a couple weeks back, and I think it's a nice breakdown for one way of thinking about how to, I guess, have a map for what are the kinds of things you'd be looking at within quantum machine learning. So one way you can kind of break it out is thinking about the types of algorithms you'd be running or the types of data that you'd be running it on. We tend to focus at Righetti on things that fall in this space probably. So we're interested in using quantum algorithms on classical data, because it turns out if you talk to a bank or an oil and gas company, they have a lot of classical data and they want to get some kind of a speed boost using quantum. But there's also really improvement areas within each of these sections, and we'll touch on this a little bit in this talk. But there are active research areas for using classical algorithms on quantum data, for instance, to try to improve or do error correction at the hardware device. So using classical models to improve how we're using the quantum hardware. And we also have some quantum-inspired techniques, which could kind of be thought of as a classical algorithm that takes inspiration from the quantum world and still ran on quantum data or classical data. Another way of thinking about how to break these out again is by like the use cases again of what people would actually be trying to do with these models. Seth has already brought up, famous HHL algorithm and some others that was sort of like a first wave of what you'd be doing with quantum machine learning. Grover's was also another thing that a lot of people figured out had application in doing things like k-means and things like that. But again, some of these just won't be quite as amenable to near-term devices. So some of the use cases now that are popping up with sampling or classification, synthetic data generation, are all taking advantage of various flavors of these parameterized quantum circuits. So one of these is the example of quantum kitchen sinks. This is a work published by Righetti last year. And basically, a common thing, I guess, within the field of quantum machine learning is step one, maybe think about a classical machine learning model and think about how you might make a quantum variant of that. So there is a classical algorithm called random kitchen sinks, basically. And the idea there is that you will take sort of a bath of things that can perform nonlinear functions, put your data through that, and then on top of that, you can build an easier to train linear model that you might be able to have extracted some nice features from those kitchen sinks, right? So the idea here that Righetti did is basically let's do a quantum version of that. So we have kind of a high, this is sort of the model at a high level. We have some input data U, and we're going to process that through a whole bunch of parameterized quantum circuits to get some quantum nonlinearity out of it. And then on top of all those results, once we've used the quantum to sort of to pre-process our data and create these features, we're going to have a simple linear model that we're going to stick on top and train and see how this performs on a classification task. So here's kind of the more detailed version of what this looks like. The classical data gets encoded into rotation angles, right? So again, this is where the parameterized part comes in. They get programmed into these angles of the rotations in the quantum circuits, and you can tune those things to reduce some loss function. And these are some examples of ansatz that were explored in this particular experiment, which was to classify, I believe, the digits in MNIST, who I assume we're familiar with like MNIST here a little bit, but it's a big data set of handwritten digits between 0 and 9. And this experiment was just trying to classify 3s versus 5s. So they were not looking at the full image data set, but they were trying to create a model that could distinguish, I believe, between the digits 3 and 5. And what they saw was that indeed using these sort of features derived using the quantum kitchen sinks, there's error here on the y-axis, and the red line at the bottom is 1% error, so you'd like it to get closer and closer to that, which was done using just a classical support vector machine. And what we see in the blue and orange lines using the quantum approach is that these quantum systems are able to extract meaningful features, and they're able to approach sort of the classical performance, but they weren't seeing a huge benefit yet over what was done classically. So this is kind of, again, circling back to this constant question that we're all trying to probe a little bit is like, where's the utility of these quantum systems? This is very cool that we've shown this is feasible, but we want to keep trying to drill and show again that there's like a true benefit of doing these kind of quantum approaches. A more detailed version of this that I had published this year and that has gotten accepted for publication within the Quantum Machine Intelligence Journal is a very sort of a building on this kind of quantum kitchen sinks work. And to kind of understand how the algorithm works, I want to make sure everyone here is familiar with convolutional neural networks before jumping into the quantum variant. But kind of one of the thoughts I had previously was, there's a lot of these interesting models, but we also want to see how they might fit as more of like a subroutine within a really known powerful classical machine learning model. So for those of you that aren't super familiar on CNNs, they're really like they're sort of known as the standard within many image recognition use cases. And the way they operate is that they take input images typically, wherein each pixel or pixel within a color, like an RGB map, gets mapped to an input neuron, and then these subsamples of your input data are run through these classical convolutional filters. And what these filters are trying to learn are different levels of abstracted features. So kind of here you can see that like at the lower layers in this stack, you're taking pixels with particular values, and then you're sort of getting features that learn to identify lines at different angles. Those then become the new sort of input neurons that are then learning basic shapes, and on up the stack, each of these neurons is sort of learning to extract features that have higher and higher sort of abstract value. Then when you get new data, you're basically looking at these high order features, and you're trying to have basically train your model to have a really high correlation with particular features and a particular outcome. These models are really powerful, and they can be trained via backpropagation, which is nice. But we wanted to see if adding quantum sort of into this mix could provide some kind of benefit or modeling capability. So my clunky portmanteau here is, let's do this convolutional neural network algorithm where the nice thing here is it's very NISQY. Again, convolutional neural networks, they are only looking at subsamples of your input data. So instead of having to jam the entire thing on at once, you're basically piecewising, taking it apart, and only mapping those pieces individually to this quantum version of a convolution. What the convolution does is that it takes your input data and it does like a basis encoding basically into a parameterized quantum circuit, runs it through that circuit, and then we can decode out a single scalar value just like a classical convolutional filter. So it integrates exactly like it would within a classical framework, which is nice. And the, again, kind of hand-wavy thing here is why this could be interesting is that we know these quantum circuits are able to do more powerful transformations than you could do classically. So if you can find an example where the quantum is giving you a performance benefit over classical, you know that you're not going to be able to simulate these kinds of quantum transformations at scale. So there could be a weak form of like benefit there, essentially. So again, these are going to be coming out next month in QMI, but they're available in the archive right now. What we saw quickly here is as we trained the convolutional versus the convolutional neural networks, the quantum one's like up here in green, they were able to achieve almost like a perfect accuracy on the full MNIST data set, so not having to do a lot of reductions and things like that. And they were able to kind of converge on this with fewer training iterations, which was nice. The problem is when we compared them to, again, adding essentially additional classical nonlinear processing, it still wasn't distinguishing itself from this like red line, essentially. So we're building more powerful models, but we're still really looking for this like true benefit yet. So this is an active area of research that we're looking into. Maybe there's particular data sets or encodings or types of ansatz that just work better than others. So that's an active area of research. The last thing I'll talk on real quick is we're not just doing classification tasks using the PQCs. We also are doing some work within the quantum-inspired space. So I was actually part of a company, QBranch, which Righetti bought. We're now primarily the applications team at Righetti. And something that we had built at our company before was a very large quantum annealing simulator. So this is basically a different flavor of quantum computing that's more based on an energy-based model. It turns out that these particular types of quantum computers, or simulated quantum computers, natively sample from a Boltzmann distribution, more or less. And for those, again, familiar in the machine learning community, Boltzmann machines can be some really powerful models, but up until more recently, they basically didn't have good tractability in terms of training because there's a step within the training algorithm to figure out the weight updates. You need to make an estimation over all possible model states. Essentially, you need to know the partition function, which as the number of neurons goes up, 2 to the n doesn't scale very well, right? So the idea here is what if we just map our energy function onto this sort of simulated framework, which just natively draws samples which already obey this partition function rule, more or less. And we can use them to train not only fully connected Boltzmann machines, but also ones with hyperedges if we can reduce the edges down. So anyway, this is some work we showed at QTML, basically taking a financial use case, so market data, and trying to generate new market data, which is nice because that's like a use case people would care about, don't have to worry about public, personal information getting leaked out if you're using synthetic data. And we compared this actually to quantum annealing devices built by D-Wave, which is actual quantum hardware. And what, again, going to go through this pretty quickly, as we trained our models, basically our simulated ones are in blue, and they were able to trick an adversarial model, which is trying to detect if you're generating fake or real financial data. And not only was it able to get to basically trick this model, it was performing really similar to real quantum hardware. And the nice part is for us then, we have this interesting quantum-inspired technique, which can simulate 32,000 fully connected quantum annealing qubits. So we can start investigating with this quantum-inspired technique some really interesting sized problems. These are also some examples of totally synthetic data generated by models trained using our quantum simulator and on the MNIST data set. So these are like what our quantum models were able to learn just based off of being fed totally unlabeled data and trying to learn these patterns through unsupervised learning. And finally, this last slide, this also has a relevancy back to, again, Righetti's core kind of values of doing these circuit-based quantum models, because there's a very similar model to the Boltzmann machine called the quantum Born machine, which is also very good for doing generative modeling. Here's some example of a paper which showed that you could use this kind of thing to generate bars and stripes data. But so anyway, we think that in the meantime, we're also going to be looking into training these models using our actual quantum hardware. And then we have a nice comparison between sort of a very different simulated model and the real hardware stuff. So kind of flying through some of the applications there at the end, but hopefully this paints a little bit of a picture of some of the quantum machine learning work we're doing at Righetti, and as well as how our hardware and software are kind of coming together to help our users. And feel free to reach out to me or Amy if you're interested in getting access to some of our systems, or visit us on the web, Google Righetti Force, and I'm sure we're going to pop up. So thank you.
Questions for Max?
Two questions. So what would you say is the conceptual difference between this quantum kitchen sink idea and reservoir computing?
Mm-hmm. And what was the...
Reservoir computing?
Yeah, gotcha. So the idea, or the question here is, what's the difference between the quantum kitchen sinks and reservoir computing? That's actually the perfect, they're very similar conceptually. The difference really is that, kind of similar to what I talked about for the convolutional algorithm, is that the nonlinear, sort of the functions fundamentally that the quantum circuits could provide might be more powerful than some of the other classical implementable ones, but it's fundamentally the same idea, where essentially you have like a reservoir of nonlinear functions, and you're trying to learn the mapping between those to some particular output. Yeah, but it's very similar.
And then I was also hoping if you could talk about the motivation behind the topology for the Aspen chip.
Yeah, so I believe that's primarily influenced by, and there's, so again, not a hardware expert, but sort of, Will might actually have a better answer to this. But yeah, I think it's primarily for sort of scalability. You have to feed in signal into the chip in a particular way, and I think this was chosen because up to like 1,000 qubits it scales out. Up to a very high qubit count, it scales nicely before, running into problems. But yeah.
And the only thing I'll add, so that's a big part of it. The hexagons are nice to stick the readout resonators inside, because you've got a lot of room in there from a physical standpoint. But from a quantum error correction standpoint, you can also fit a 488 color code on it. So that's nice.
And also the connectivity per qubit, not too many qubits connected, so it helps with the trying to avoid collisions in the frequency split.
Yeah, the degree of that.
You got that guy.
Yeah.